Astronomers and physicists are still very interested in and studying black holes, which are one of the most mysterious and interesting things in the world. The strong gravitational pull of these celestial objects and their total lack of light emission make them a boundary beyond which the known laws of physics no longer apply. Einstein first thought of black holes in 1916 as a result of his theory of general relativity. They were only thought to exist until technology progress made it possible to indirectly find them in the middle of the 20th century. In the 1960s, scientists studying the constellation Cygnus found a strange object in the sky, a bright blue star giving off high-energy X-rays. This was the turning point. This star's orbiting around an invisible partner didn't make sense until it was found to be locked in a gravitational embrace with Cygnus X1, a very large black hole. Cygnus X1's finding proved beyond a doubt that black holes exist and began a new era of research into these mysterious objects in space. Cygnus X1 is about 6,000 light-years away from Earth and has amazing qualities. It is very dense and has such strong gravity that not even light can escape its grip. The name black hole comes from this trait, which sums up what these strange things are all about. Later studies have found that there are many more black holes spread out in the universe. It is thought that the Milky Way galaxy may contain more than 100 million black holes, though it is hard to be sure because they are so hard to find. Astronomers have found many possible possibilities in our galaxy, ranging from stellar mass black holes that form from the remains of very massive stars to supermassive black holes that live at the centers of galaxies. Black holes' gravitational pull goes far beyond their immediate surroundings, changing the way galaxies evolve and what happens to matter in their path. If something gets too close to a black hole, it will be sucked into it and will not be able to escape. It will pull it toward the event horizon, which is the point where it's impossible to go back, where it will be sucked into the black hole's singularity and be destroyed. This terrible process, called spaghettification, is the ultimate example of how powerful a black hole's gravity is. As an item gets closer to the event horizon, the difference in gravity along its length gets so big that it stretches and warps into a structure that looks like spaghetti strands. The black hole's forces are stronger than the bonds inside the object that hold it together. As a result, the object breaks apart into a stream of matter that will eventually join with the singularity. Even though black holes are interesting because they can be used as cosmic labs to test the limits of physical theory, they are still very mysterious and interesting. The search for their secrets hasn't stopped because people want to understand how space, time, and gravity work at their most basic level. Black holes are like quiet guardians in the vastness of the universe, calling people to explore the depths of the unknown and learn more about the world. Though the nearest black hole is a very long way away, about 1,500 light-years, people are still curious and worried about what might happen if they collide with us. In 2021, scientists took the first clear picture of a black hole, named M87, and found at the center of the M87 galaxy. This was a huge step forward in science. This amazing accomplishment gave us important new information about black holes and how they are put together. The picture data showed that black holes have many layers, which goes against the common idea that they are single entities of pure nothingness. Researchers were able to see 3 separate layers inside a black hole by carefully analyzing and putting together images. The event horizon, a key line that marks the point of no return, is at the very edge of the border. Once something goes past this point, it can't be stopped by gravity, and it will fall into the black hole without stopping. The second layer, the photon sphere, is closer to the black hole and is where light is forever trapped as it orbits it. If photons try to enter this realm, they will be sucked into the black hole's strong gravity pull and will be trapped there forever. The third and final layer, the singularity, is at the center of the black hole. This is where the rules of physics reach their furthest point. Here, matter is compressed in a way that is hard to understand, and it gets so small that it has an infinitely high density. Within this mysterious singularity, the usual rules that guide the universe stop working. This leaves scientists in a place of deep doubt and speculation. Understanding black holes is hard because they are so different from one another. Even though all black holes follow the same 3-layer structure, they all have their own unique traits and behaviors that make them hard to put into easy groups. So, standard scientific methods aren't good enough to look into these huge objects in space. so new ways of doing things are needed to solve their mysteries. The main way to study black holes is still through indirect observation, since direct research is impossible because of their strong gravitational pull. Trying to send probes into black holes would always end in disaster, as the relentless forces at work would destroy them. Even with these big problems, scientists are still trying to figure out what black holes are all about. Theories about their origins and behavior, from stellar collapse to galactic dynamics, give us intriguing hints. In particular, NASA's study of M87, the galaxy core, revealed strong proof of a supermassive black hole pulling matter together on very large cosmic scales. In the face of such cosmic mysteries, people will continue to seek information because they are naturally curious and want to understand. Unsolved puzzles like black holes may be hard to understand, but scientists are determined to keep looking into them. Eventually, they will discover the deepest secrets of the universe. Roy Kerr's groundbreaking work in 1963 gave us a new way to think about black holes by suggesting a theory of spinning black holes that went against everything we knew at the time. Kerr built on Einstein's theories of gravity to propose that a spinning black hole would not collapse into a singularity, but instead would take the shape of a rotating disk or ring of fire. This idea was different from what people thought at the time. Kerr's answer was based on the idea of the ergosphere, which is an area around the black hole where centrifugal forces balance out gravitational collapse and stop the disk from falling even more. In this constantly changing space, the rules of physics start to behave in strange ways, which hints at the deep secrets that lie inside black holes. But the most interesting thing about Kerr's theory was that it predicted an Einstein-Rosen bridge, which people sometimes call a wormhole. It is thought that this theoretical idea could be a way to travel through space-time, connecting different parts of the world or even different parallel universes. Einstein's theory of general relativity describes how space and time interact in very complex ways. The idea of wormholes is based on these interactions. Space and time are woven together in this way to make a four-dimensional cloth called space-time. When big things hit this cloth, they bend it and create gravitational fields that change the way matter moves around them. Wormholes basically cut through the fabric of space-time to connect faraway places in it, and they might even let you travel quickly across huge cosmic distances. There is still a lot of speculation and debate in the scientific world about how stable and useful wormholes are, though. There are some exciting possibilities for interstellar travel and exploring the past and present through wormholes, but there are also some big problems and restrictions that make these ideas more realistic. Wormholes are naturally unstable, and quantum forces and radiation make them very difficult to pass through. This makes it unlikely that they could be used as a useful way to travel. Einstein's theory of special relativity also puts basic limits on how fast things can move through space-time. This means that even if they are stable, wormholes might not allow for movement faster than light, which is a central idea in many science fiction stories. Wormholes are still interesting to scientists because they lead to new discoveries and ways of looking at things. The Kerr wormhole, named after its famous creator, holds the alluring promise of cosmic gateways and other worlds. It encourages people to think about the mysteries of the universe and the endless possibilities that lie beyond. The search for a single framework that unites the seemingly unrelated fields of quantum mechanics and gravity has led to the search for a theory of everything, a single set of ideas that can explain all the basic forces and particles in the universe. Michio Kaku, a famous theoretical scientist, is at the head of this project. His groundbreaking work has sparked interest in superstring theory. Superstring theory is very different from standard ways of thinking. It says that fundamental particles are not points, but actually very small strings that vibrate. Like the strings on a musical instrument, these strings vibrate at different frequencies, which creates the many particles and forces that we see in nature. That's why the universe is like a big orchestra, and each particle is like a different harmonic vibration of these basic strings. One of the most interesting things about superstring theory is that it can explain the strange things that happen around black holes, wormholes, and other strange answers to Einstein's gravity equations. As strings move through space-time, their changing motion causes curvature and distortion, which show up as gravity singularities and topological anomalies. Although superstring theory looks simple, it is actually very complicated because it needs more than the usual 3 spatial dimensions and one time dimension. Human sense is put to the test by these extra dimensions that can't be seen or touched directly. Though, mental pictures like fish living in a two-dimensional pond can help us understand how hard it is to reach these higher dimensional places. At normal scales, these extra dimensions can't be seen because they are compressed, like a rolled-up piece of paper curling up, but their impact is everywhere in reality. The exact nature of these hidden dimensions is still unknown, but the idea that they exist gives us a tantalizing way to explain the complex symmetry and phenomena we see in the world. In addition, the mathematical foundations of superstring theory have led to a revolution in mathematical physics, showing deep links between abstract mathematical structures and real-world events. In fact, the search for a theory of everything has brought different fields together, showing how closely mathematics and the natural sciences are connected. Even though superstring theory is very well thought out and can explain a lot, it is still just a theory that needs to be tested in the real world. Because extra dimensions are secret, it is very hard to prove them through experiments. This means that superstring theory is only useful for mathematicians. Still, the bold idea behind superstring theory continues to fascinate scientists and non-scientists alike, calling for everyone to start on a journey of intellectual discovery and exploration. As we go deeper into the uncharted areas of theoretical physics, led by the bright light of superstring theory, we face the endless mysteries of the universe. We are on the verge of a new era of understanding and wisdom. Scientists have been trying to figure out the secrets of quantum black holes for a long time, but they have been very hard to solve. They are a huge obstacle to our understanding of the basic nature of the universe. Many physicists have tried to solve this mystery, but they haven't been able to. This led Edward Witten of the Institute for Advanced Study at Princeton to call superstring theory 21st century physics that fell accidentally into the 20th century. However, recent events have given people who are trying to understand quantum black holes new hope. Not one but several groups of physicists independently revealed a major breakthrough. They found that string theory could solve the problem completely, but only in 2 dimensions instead of the 10 dimensions that traditional superstring theory suggests. Although this is a positive step forward, the search for a full solution is still ongoing. The difficult equations involved are causing a lot of problems. In our search for a single theory that explains everything, we are drawn to the deepest parts of the universe, where truth and speculation become blurry and the universe's secrets wait to be revealed. Modern physicists are looking at new ideas to help us learn more about black holes and their place in the universe. These ideas build on what Einstein and Kerr already knew. The connection between black holes and quantum physics is becoming more and more interesting, especially since trying to fit the 2 theories together leads to paradoxes. The information paradox is especially interesting because it makes us think about what happens to data when it goes into a black hole. In quantum mechanics, information can't be lost. However, matter seems to disappear from our view of the world when it crosses the event horizon. There is a lot of disagreement among scientists about this contradiction. Some say that information is stored at the event horizon itself, possibly encoded in a holographic way. This idea says that the data about things that get sucked up by a black hole might not be lost, but might be changed and kept in a different way. Stephen Hawking's idea of Hawking radiation, which came out in the 1970s, has added another level of complexity. Hawking said that black holes aren't completely black. He said that they give off radiation because of quantum processes close to the event horizon. Over astronomically long periods of time, this radiation could cause black holes to slowly disappear. This raises more questions about their long-term fate and the final fate of the information they hold. Also, scientists are looking into gravitational waves, which are ripples in space-time that are caused by the speeding up of huge objects, like black holes merging. In 2015, scientists made the first direct detection of gravitational waves. This started a new era in astrophysics by letting them see and study things that were previously buried. This has made it possible to study black hole crashes, which has helped us learn more about their mass distribution, spin, and how they form. As we look into these issues, progress in astrophysical models and observational technology keeps making our knowledge of black holes better. Astronomers can take very clear pictures and data with tools like the Event Horizon Telescope. And gravitational wave trackers like LIGO and Virgo give us a new way to look at the strangest things in the universe. These different projects help to build a story about black holes that forces us to rethink basic ideas in physics and the very nature of reality. With each new finding, we get closer to answering the big questions about life, the nature of space-time, and what will happen to our universe in the end.